Today we're going to talk about the first few sections of our Kinetics chapter, which studies how the concentration of reactants and products changes over time. You'll notice that our concentration of reactants always goes down over time, and our concentration of products will rise over time. Our notation for the change of the concentration over time looks like this. Where A is a reactant and B is a product. We'll use the symbol delta for the change in A over the change in time. Or if you're talking about the instantaneous rate of change, you can talk about the derivative using a little d for our change. These changes will be equal to the rate of the formation of the product. Notice how the rate of the formation of the product is a positive because these numbers are going up over time. Now this gets a little bit more interesting if you have a more interesting equation than one thing turning into one thing. For example, let's say we have the reaction of nitrogen dioxide gas decomposing into nitrogen monoxide gas and oxygen. In this case, we have some interesting coefficients. We have these 2's and a 1 in front of the oxygen. Let's label our reactant as black. If this one happens at this rate over time, the nitrogen monoxide should also follow the same exact pattern. We'll label this one to be red. I'll do my very best to sketch this appropriately. Now, our last and most interesting piece is going to be what happens with the oxygen gas over time. Since that one has one molecule for every 2 forming, we're actually going to see that one happen half as fast. Now we can write our rates with mathematical representations that takes into account how the stoichiometric coefficients are going to affect how fast one species is forming or decomposing in relation to the other ones. All you have to do is take the number from the coefficient and turn it into a fraction. Just remember that all of the reactants are going to be negative because those are going down over time. And all of the products are going to be positive. Notice in this last one how I have a 1 over 1 fraction, so I can just write the change in the oxygen gas over time. Now we can use these relationships to answer simple questions about how one rate of a particular chemical in an equation is related to another. For example, using our previous example of 2 nitrogen dioxide molecules turning into 2 nitrogen monoxide plus 1 oxygen molecule. If the rate was negative 4.2 times 10 to the negative 5 molarity per second for the nitrogen dioxide, what was the rate of oxygen gas appearance? Now we can use our relationships from the previous slide. Remembering that this chunky expression of the dNO2 over dt This whole entire symbol just means rate of that thing. So don't worry too much about the notation. And what we're trying to do is we're trying to isolate what this factor is. What is the rate of appearance for the oxygen? If you look really closely, all we have to do is take this number right here, the negative 4.2 times 10 to the 5, and stick it in right here. Because that's what that rate means. It's that mathematical expression. So we'll put the negative half, negative 4.2 times 10 to the negative 5. And we'll get a positive number now because 2 negatives makes a positive. And that'll be 2.1 times 10 to the negative 5 molarity per second for the oxygen. Now this makes perfect sense if you think about it. If we have 2 nitrogen dioxide molecules forming every time there's only 1 oxygen, it should be twice as fast. The oxygen is forming half as much. So the number for the rate should be half as big as it is for the other product. And that's how you solve most of the problems for the first 3 sections of this chapter.